9-4. So we're going to take our sequences that we did the other day and we're going to turn them into series. So we're going to do finite and infinite series. You're going to need your calculator, so make sure you get that out. I'm going to teach you how to do some of this on your calculator. You don't have to use your calculator, so it's kind of like a bonus. If you want to use it, you can. Mine's over there. Great. Okay, we have, here we go, some parts. Letter A. Let's go ahead and first talk about a little something called summation notation. Summation notation is going to be our sigma. Remember this? Yeah. So we have summation notation is a capital letter S. It's a Greek letter. It's called sigma. And what this means, it means to evaluate the sum. So if we start, for example, k equals 1 to n for a sub k, okay, we have some explicit formula in here. K equals 1 is our starting point, n is our ending point. So this is a finite sum. It has an ending point. What happens is we plug 1 in and we get a sub 1. We plug 2 in for k, we get a sub 2. We plug 3 in and we get a sub 3, and we do that all the way until we plug in n. And then we add them up. Okay, do you remember doing this in Algebra 2? Yeah, it's just taking the first term plus the second term plus the third term of a sequence all the way to n numbers of terms. So let's go ahead and do some. Let's evaluate. Number 1. I do not teach this in Algebra 2, but there is a button on your calculator. Some of you guys found it last year, sneaky people. But I don't mind you using it. I'll show you where it's at if you don't know. So here we go. We're going to evaluate the summation of k equals 1 to 5 for 3k. Okay, we can do this by hand. I'm going to show you how to do a formula later for this. But we can do this one by hand. You just go ahead, you plug 1 in. And so the first term of this series would be what? 3. Then you plug in 2 and you get 6. And then you plug in 3 and you get 9. Plug in 4, you get 12. 4 times 3 is 12. And then you plug in 5 and you get 15, and that's where you stop with the numbers. So this is called a series. A series has pluses in the middle instead of commas. A sequence is commas, and a series is pluses. And so you go ahead and you figure that out. Beep, boop, beep, boop. And what do you get? 45. Okay? So that's the answer to that problem. It says to evaluate, you need to know what sigma means. It means the sum. Now, go to your calculator, and I'll show you where it's at. Especially if you have a new calculator. I'm sorry, Lucas, and others with the TI 83. This doesn't work on there. Okay, so you could go to alpha window. That's always a good shortcut. And if you see it there, it's number 2. See it, number 2? Oh, Molly, you too, huh? You know, it makes a really good stocking stuffer. You can ask your parents. No? Okay. Or Santa, I'm sorry, freshman. Oh, no, there's no freshman here. Okay, we're okay. All right, x equals 1 to 5 for 3x. Okay, and then you hit enter, and guess what? Boom, 45. I know, sigma notation. You remember that?
Yes.
Yeah, you do. Stephanie. I was like looking that way. Did you sit over there? No. Okay. All right. Good. Good too. All right. 45. Pretty easy, right? Isn't that nice? You like it? Yeah, it's good. Okay. If you don't have that, you know, there is a YouTube video out there that shows you how to do it without this sigma notation. You go to math and it's like sequence or something, or I don't know where it's at. But, oh, I think it might be under stat. No. Okay, never mind. I'm not sure, but you don't need it, is what I'm saying. Okay, let's do another one. Letter B. Let's do the sum k equals 5 to 8 for k squared. See, these are such low numbers of numbers that you're adding up that you don't need to put this in your calculator. It might even be faster if you just do them, right? Okay, so we're going to go ahead. This time we're not starting at k equals 1. You can start at k equals whatever. Here they have you starting at k equals 5. So your first term is to plug 5 in, and you get 25. Your next term would then be to plug in 6, and you get 36. 7 will give you 49, and 8 will give you 64. Now, those of you who have a fancy calculator, did you figure it out? What'd you get?
Oh, I didn't.
You didn't do it? Oh, I thought you were. You were going to? You changed your mind? Yeah, that's all right. I'm going to go alpha window, number 2. X equals 5 to 8 for x squared. 174? Yeah, good. Okay, now notice real quick, though. Notice how many terms I added up. Do you see how many? 1, 2, 3, 4. When you're adding up numbers from 5 to 8, a lot of people think there's only 3 numbers from 5 to 8. But you know what they do? They're doing 8 minus 5, and they're getting 3, but they're canceling out 5. So from 5 to 8, there are 4 numbers. So if I ever ask you something like, let's add up the numbers from k equals 12 to 58, and you want to find out how many numbers that is, you would do 58 minus 12, but then don't forget to add 1 back on. Okay? It's a real nice way to do it. All right, so that's summation notation. Everything today is really just Algebra 2 review. It really is. Okay, let's go on to part B now. Now we're going to do arithmetic sums. Okay, we'll do some geometric and arithmetic. Geometric, that's the trickier one. It's going to have 2 different sum formulas. Arithmetic only has 1. It only has a finite sum formula. Okay, because with arithmetic, you can't add up an infinite amount of arithmetic numbers because then it's just going to go to infinity. All right, so here it is. I'm going to go ahead and tell you, if you have an arithmetic sequence, and it's a sub 1 plus a sub 2 plus a sub 3, all the way to a sub n, which is your last term, then the sum is going to equal the sum of n numbers equals, you take the number of numbers that you're adding up, so maybe there's 10 there, or 20, or 25, or whatever. You're going to divide that by 2, and you're going to take the first term plus the last term. Okay. Do you remember that formula? It's an Algebra 2 formula. There we go. We're going to use this for arithmetic finite sums. Now, I think I told you this story last year about my favorite mathematician, Friedrich Gauss. Do you remember him? Yeah. And he ended up adding up 1 plus 2 plus 3 all the way up to 100. And when he was 10 years old, his teacher told him to add those numbers. Quite a story, huh? And what he did was he ended up putting them backwards like this. This is in your book. Actually, there's a whole paragraph. And then 98 all the way to 1. And so when he added these up, he got 101 plus 101 plus 101. And he got that how many times? 100 times, right? And so he did 100 times 101, except that he added up the sequence twice, so he needed to divide by 2. And that is exactly the formula that we do. See the formula? It's 100 numbers divided by 2, the first number plus the last number. Isn't that incredible? He was 10 years old. Yeah. It's all right if you're not that smart. I'm not either. It's okay. He was like a genius in the math world. He came up with a lot of stuff. He's really cool. All right, there is a different formula that your book gives you, which I don't care for very much. They give you this one down here. So this formula right here, the problem that people have with it is, what if I don't know the last term? You know, that's sometimes a problem. So they give you this option of doing this formula. S sub n equals n over 2. And then what they do is they take a sub n and they substitute it for a sub 1 plus d times n minus 1. So you get 2a sub 1 plus d times n minus 1. I don't like it. It's clunky. Yeah. I'll give it to you, though. If you want it, you can have it. Some people like it. I don't know. Sometimes I don't like to say I don't like something because it sways you. I know it does. It does. You're like, oh, I don't like it either then. Or maybe you're like, no, I do like it. I don't know. Maybe you're one of those people. All right, here we go. Number number 2. So let's go ahead and practice. Let's do this. Let's do something like this. Let's add up the numbers from k equals 1 to 50 for 2k minus 4. All right, so first of all, if you have your calculator, you know, go ahead, use it. That's great. Some of us don't have that calculator, or maybe I might ask you to use the formula to solve it or something. But I wouldn't have you write out 50 numbers, that's for sure, okay? So if you notice right away, this is linear. And anytime you have a linear explicit formula, it's going to be arithmetic. Okay, we know that, it's arithmetic. So I can use the arithmetic sum formula. So here we go. How many numbers am I adding up from 1 to 50? There are how many numbers? 50 numbers, okay? And then the first number is not, okay, so wait, hold on. So 50 over 2, the first number is not 1. People make that mistake. The first number is to plug in 1, and what do you get for the first number? -2, good, thank you, Cameron. And then plus, the last number is to plug 50 in. 2 times 50 is 100, minus 4, so 96. Okay? And then you just go ahead and use your calculator. And you go 50 divided by 2 times -2 plus 96. 2350? Yeah, nice. Okay, or you could, you know, use your summation notation on the calculator. It'll do it for you also. All right. Number 3. Here comes a classic problem. You're going to like this one a lot. I do this at weddings when I'm bored. I like to think, how many seats are there in this wedding ceremony? You know, how many people are allowed to show up? So here we go. Let's say that we are sitting in chapel or a big stadium or something, and we have 8 seats in the front row. 8 seats in the front row. And then each row has 2 more than the one before it, okay? Each row has 2 more than the one before it, than the previous row. Previous row. My stylus isn't very good today. Okay, and then let's say that there are 30 rows total. So the question is, how many seats are there in this chapel? How many total seats? Okay? All right, I'll let you catch up on that. And then we're going to write the series out. Sometimes it's nice to take your word problem and turn it into just numbers. So we'll do that. Okay, so the first row has 8, so I'm going to write 8. And what does the next row have? 2 more than that, so 10. And the next row has 12 and 14 and blah, 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 all the way until I don't know what the last row has. But I do know that there's 30 of them, okay? So let's go ahead and write our sum formula. This is arithmetic because it's adding 2 each time, so it's arithmetic. So I would go 30 rows divided by 2. First row has 8, last row has, I don't know. Okay, we can figure that out though. You know how you figure that out? If I want the 30th term of an arithmetic sequence, what do? I go up to its explicit formula and I'll plug 30 in, right? So we can make an explicit formula for this. The explicit formula would be a sub 0 plus dn. Yeah, it's going to use the stuff that we already did. So this would be, what would a sub 0 be? 6 plus 2n. That's the explicit formula. If you don't like that formula, use the other one. It's fine. It'll get you there too. You could do 8 plus d times n minus 1. And now let's find out what the 30th term is by doing 6 plus 2 times 30. So how many seats are in that last row? 66. Good. 66 in the 30th row, so I'm going to plug in 66 right there. Now in Algebra 2, you might have made the Algebra 2 mistake that kids make. They plug in 30 for this number right here, but that's not how many number of seats are in the 30th row. Okay? You plug 30 in to find out that there's 66 seats. Did you like this chapter back then? Note to self, nobody said anything. All right, so you get 1110. 1,110 seats. Okay, let's do one more of these, and then we'll get to our geometric series. Number 4. This one's a little different. Here we go. 5 plus 16 plus 27 plus 38 plus ... plus 1644. All right. So this one, we're going to write summation notation for this. So we're going to put this into a sigma, summation notation, and then we're going to evaluate the sum. Evaluate the sum. Okay. Now, the last problem, they left out the last number. This problem, they're leaving out how many numbers there are. They like to leave something out. They like you to do some work, you know? So here we go. Let's first write this in summation notation. In order to write this in summation notation, you need to have an explicit formula for this, okay? So our explicit formula for this sequence would be that I'm adding, it looks like 11 each time, yeah? And so I'm going to use the a sub 0 one, and I'm going to go back 11, so that would be -6 plus 11n. Okay? If you want to rewrite that, you can. You can write this as 11n minus 6. That looks nice. And then start at n equals 1. Make it easy on yourself. And check it out. If you plug in 1, you'll get 11. If you plug in 2, you get 16. Like, test it to see if it works. Now, the problem is I don't know how many numbers I'm going to add up here. So this is what you're going to do. It's a little different. We need to find out what n is. We know that the last term is 1644, and I'm going to plug that in for a sub n and find out what term that is. Ooh, it's the other way, isn't it? Last time I had to plug it in for n, I had to plug in 30. This time I'm given the last number, so I plug that in on the other side and solve for n. So I'm going to add 6 and divide by 11. What'd you get? Anybody? Be brave. What'd you get? 150. Thank you. 150 terms. Okay? So we get 150 goes in the top of this sigma notation. And now I want to find the sum of the first 150 terms. And so I can either use my calculator, which go ahead, I'm not going to stop you, or I can do just the sum formula for arithmetic would be 150 over 2, first term plus the last term. Let's see what that ends up being. Times 5 plus 1644. Let's see if you got it. I got 1, 2, 3, 6, 7, 5. Yep. 123,675. Huh, crazy, that's my salary. Just kidding. In smiles. See the smiles? Yep. Okay. Now, let's move on. Part C. Are you wondering how many parts there are? There's just 2 more. So we're going to do geometric finite, and then we'll do geometric infinite. Do you need a little stretch break, or you want to just plug on through? We're doing okay? All right. Geometric finite. Do you think Jake's going to watch this? Jake's not here today? No? Okay. No shout-outs then. All right. Geometric finite sum. Now the finite geometric is really kind of complicated. It's a complicated formula. And the infinite is very simple. It's kind of weird. So here it is. If you have a geometric sum, a sub 1 plus a sub 2 plus all the way to a sub n, okay, it's the same idea. You're adding up numbers, except that it's not arithmetic anymore, it's geometric. Then the sum of the finite numbers is equal to, you're going to do a sub 1, the first term, times 1 minus r to the n over 1 minus r. All right, you were given that formula last year. Maybe you recognize it. Maybe you've, blocked it out of your memory, where all the bad memories are. Okay, so here we go. Let's do one. Are you ready? Ooh, this one's tricky. Should we do the tricky one first? No, let's do the easy one first. Number 5. So number 5, let's do this. Let's go with negative 1/4 plus 1/16 minus 1/64 plus 1/256 plus ... And we are going to find, so this is an infinite series right here, but we're going to find the 9th partial sum. Yeah, that's weird, huh? It's weird wording. In other words, we want to find just the sum of the first 9 numbers, okay? It's a partial sum. This sum goes on forever and ever and ever because it says ... it doesn't end. But we just want to find the first 9 numbers. All right, so we can use our formula, or if you want to, you can make an explicit or summation notation and plug that into your calculator if you want to. But let's just use the formula here since we have it. We're going to find the sum of the first 9 numbers. And we're going to do a sub 1 is negative 1/4 times 1 minus r. Oh, bless you. What's r in this case? Negative 1/4. Yeah, it's a sub 1 and it's r. So then it's negative 1/4 to the 9th power. I put that in parentheses, and it doesn't matter here, but if that was a positive, or if that was an even number to the 8th, it would make that positive. So you got to be careful. Put that in parentheses over 1 minus negative 1/4. Okay, I think the formula is okay, and it's not too bad, but plugging it in your calculator, a lot of people will then get it wrong, and I don't know why. So let's check this out. I would just plug the whole thing in. I would go negative 1 divided by 4 times parentheses 1 minus parentheses negative 1 divided by 4, close those parentheses to the 9th power, and then close the parentheses up top, divided by parentheses 1 minus negative 1 divided by 4. I didn't even hit enter. I put the whole thing in. Make sure you use parentheses up top and the bottom, and you should get an ugly, ugly number. Does that change into a fraction? Nope. Negative 0.200007629. There you go. Okay, lovely. There it is. All right, let's do one more of these. Number 6. Let's say that I have 4 4/3, 4/9, 4/27, all the way to 4 times 1/3 to the 10th power. Gross, huh? My stylus isn't working. All right, to the 10th power. I'm going to write this in summation notation, and then I'm going to evaluate the sum. Summation notation, and then evaluate the sum. Okay, so in order to write this in summation notation, I need to recognize that this is a sequence. I'm going to write its series, its related series in summation notation. I need to recognize this is geometric, first of all, okay? A sub 1 is 4, and r is what? What's being multiplied each time? 1/3. Perfect. And so when I write this in summation notation, I get a sub n equals 4 times 1/3 to the n minus 1. Okay, so I have to have an explicit formula first, and then I can go to here. So I'm going to go from 4 times 1/3 to the n minus 1. I always start my summation notations at n equals 1, and I try to check it. If I plug in 1, I'll get 1/3 to the 0, which is 1 times 4 is 4, and that is 4. And then be careful because the last number is not 10. What is the last number? Or how many terms are there? It's actually 11, if you're going to do it this way. See how this is to the 10th power right here? Plug in 11. 11 minus 1 is 10. You have to be careful. Now, if you didn't want to do it that way, you could do summation notation, start at 0, okay? But then you're going to have to use a sub 0 formula. There it is. on the board, which would be 12. No. Yes. 12 times 1/3. No. You start at 1 still, right? Yeah. Yeah. You would start at 1. Start at 1, and it's 12 times 1/3 to the n. Sorry. I'm trying to figure that out. See, when you plug in 1, you got to get 4 here. And then this would be then to the 10th power, or to the 10. Yeah. Okay. That's weird, though. I don't like that. See? I struggled through that. Meh. I'm going to cross that out. But if you want to do it, go ahead. I'll mark you right. All right, now let's evaluate the sum. Do you want to do this one on your calculator? Those of you who have, you know, nice fancy calculator. Hopefully I'll get one someday. Let's go to alpha window. Or you can use the formula, the summation formula for geometric. And we'll go x equals 1 to 11. And then I'm going to go 4 times parentheses 1 divided by 3 raised to the x minus 1. And it gives me, 5.999999. Is that what you got? Yeah? 5.999966613. It's pretty good. Let me go ahead and use the summation formula for those of you who don't have the calculator. So it's a sub 1, 1 minus 1/3 to the, how many numbers? 10. 1 minus 1/3. Should come out the same. Okay, now that kind of brings us to something here. You're probably thinking, well, is this ever going to get to 6? Or maybe you aren't thinking that, but I am. And actually, this does get to 6. When you go to an infinite number of numbers, it will be 6. If I went to my calculator and I plugged in not 1 to 11, let's do 1 to 100. Okay, I'm going to make my calculator add up 100 numbers. It takes a little time for your calculator to think about it, but I'm pretty sure it's going to give me 6. Yep, it gave me 6. Okay, so that brings up the next part, which is going to be infinite. This is the last part of today. Is this letter D? Yeah? And we're going to talk about infinite series. Infinite series. Now, yeah?
Is that sum technically an asymptote? That is, the sum actually isn't 6, but so close to 6
Yeah.
calculator.
Exactly. Yep, that's exactly what it is. Yeah, so what happens is, if your series converges, if it is a converging series, then it will have an infinite sum. Just like how you said the asymptote thing. Okay? If it diverges, it's not going to have an infinite sum. So basically, what they're going to ask you for is it doesn't happen with arithmetic sequences. It's only going to happen with geometric sequences in our cases. Okay? So for example, if I had something like this, and I told you to add up, so this is number 7. I told you to add up these numbers. Add up 0.3 plus 0.03 plus 0.003 plus ... forever. Okay? It's kind of nice when you write it like in a column too, because you can see what's happening here is I'm basically just adding on a 3 at the end. So when you add these, you get 0.3 plus 0.03 plus 0.003 plus, and you do that an infinite amount of times. What does that equal? 1/3. Okay? And so that series converges, and so you get 1/3. All right, the book's going to talk about partial sums, so I want to bring that up real quick. And then we'll do some of the infinite, and then we'll be done. So we have 10 plus 20 plus 30 plus 40 plus ... Okay. Obviously, this series is going to diverge. The numbers just keep getting larger and larger. But they are going to ask you to find the first 5 partial sums. And I don't want you to be alarmed when you see it. It looks kind of weird. The first 5 partial sums is basically just you're going to do the sum of one number, then you'll do the sum of two numbers, and you'll do the sum of 3 numbers, 4 numbers, and then 5 numbers, okay? And they write it as in a bracket type of thing. So the sum of the first number, one number, partial sum, would be 10. Okay. The sum of two numbers would be what? 30. You're just adding up the first two numbers. The partial sum of this infinite sequence for 3 numbers would be 60. The next one would be 100. And then the last one for the 5 partial sums would be 150. And then they write it in brackets. So if you see that in the back of your book and you're like, what is this? You don't have to write it in brackets if you want to write them all individually. But this is S sub 1, S sub 2, S sub 3, S sub 4, and S sub 5. This is the sum of those numbers, okay? All right, so let's do one now that you're going to get an infinite. So here we go, infinite geometric. Infinite geometric. Now, it has to follow a certain rule. The absolute value of r has to be less than 1, okay? So r needs to be a small fraction, not an improper fraction like 8 over 5. I know that's a fraction, but that's not less than 1. You need to have r needs to be like 1/2 or -1/3 or 4/5, okay? It's got to be a number between -1 and +1, but not 0. Okay, r is going to be one of those. And then you will get an infinite sum, but only if r is, the absolute value of r is less than 1. So here's the infinite sum formula. You take the first term and divide it by 1 minus r. Okay? And infinite sums really bother some people because they don't believe in them. Yeah, kind of like Santa. My son asked me yesterday if Santa exists. I told him to ask his teacher. I didn't want to lie to him. All right, here we go. So if you have something like this, we'll see what she says. And I'm going to add up 1, and then I'm going to add up half of 1, and then I'm going to add up half of 1/2, which is 1/4, and then I'm going to add up 1/8, and I'm going to add up 1/16, and I'm going to do this all the way out to infinity. Okay. I'm going to show you, I'm not using the formula, I'm going to show you a picture diagram of this. I showed this to you in Algebra 2. 1 is one full circle, right? 1, okay? Then I'm going to add another half of a circle, okay? Then I'm going to add 1/4 of a circle, and 1/8 of a circle, and 1/16 of a circle, and 1/32, and I do that out to infinity. If I stop short, I will have a little sliver here. But if I do it to infinity, it actually fills in the entire circle, and the answer of the sum would be 2. Yeah. But it's hard for our finite minds to wrap around that. Like if I said, let's walk to the door, and let's just take half the distance each time, we'd never reach it, because we're finite. If we did an infinite amount of times, we're at the door. So it's because it goes to infinity. That's why it has a sum. All right, so let's do the sum formula for that. The sum of infinite numbers, a sub 1 is 1. 1 minus r is 1/2. And then you get 1 divided by 1/2. How many halves are in 1? 2. So the formula works. We see it visually here with circles, little kindergarten diagrams, but then we also see it as a formula. Okay, so let's do number 10. Don't let them trick you, though. I'll show you what I mean by tricking you. They'll do something like this. By they, I mean me. Don't let me trick you. I'll go n equals 1 to infinity, and I'll go pi over 2 to the n, and I'll say find the infinite sum of that. And a lot of people, they'll go and they'll do a sub 1 would be pi over 2 divided by 1 minus pi over 2, and then they'll get it wrong. They'll get an answer, but it's a wrong answer, because what is pi over 2? Yeah, it's 3.14 divided by 2. It's about 1.57. Is that between -1 and +1? No. So this doesn't work. There's no infinite sum. Okay, you have to check r. You have to check this number here. Is it 1.57? Yeah, something like that. Okay, so let's do one that does work. Last one of the day. Let's do the sum from n equals 0 to infinity. And we'll go -4/5 to the n. All right, so this is a geometric series here. It's geometric because it's exponential. Arithmetic is linear, geometric is exponential. And we need to find the infinite sum. You don't need to start writing them out and doing that, okay? This isn't going to take you forever because you're adding up an infinite amount of numbers. But well, that's a little joke for you. What you are going to do is just use the formula. So the formula is to find the first term, and the first term is what? 1. Plug in 0. You plug in whatever number this is to find the first term. So I get -4/5 to the 0 is 1. 1 minus -4/5, because -4/5 is r. This formula is actually this one right here on the board. Okay? Kind of. All right, and then you go to your calculator, and you'll do, and make sure if you're going to do this in your calculator, make sure you do 1 divided by parentheses 1 minus -4/5. And you should get 0.555 repeating. Let's change that into a fraction, 5/9. Now, the cool thing about your calculator is it messes up. I know, you're like, that's cool. It is. If I go to alpha window and I try and do sigma notation, x equals 0 to 100. Okay, I did 1,000 and it was too much. You don't need that much. If you do this and you do parentheses -4/5 raised to the x power, your calculator is going to lie to you. It tells you that the answer is 5/9. Okay, at 100 it actually isn't 5/9 yet, but because it can only do so many roundings, you know, it's going to tell you the infinite. So it's kind of cool. You can check it that way too. All right.